Hello, this is our 201 in a semester project where we convert a digital filter to an LED driver. My name is Audrey.
My name is Robert.
And my name is Malik.
And you'll see in the next slide how we built, designed, and implemented our project.
The goal of this project is to take varied input sound frequencies, like those you see right now, from music and use digital filters to filter the output into distinct signals, which are fed into RGB LEDs to create different lighting colors.
This image shows the difference between a filtered and unfiltered signal. The main function of this circuit comes from the digital filter. A digital filter uses a digital processor to perform numerical computations on sampled values of a signal. In a digital filter, the frequency is represented by numbers in the code, while in analog filters, it is represented by varying voltages in the circuit. The code uses these filtered values to drive the LEDs.
The following is a list of components necessary to build a complete digital filter to LED driver.
This image shows our floor schematic or physical circuit. The component labeled FRDM-KL25Z is our microcontroller. We will break the circuit into subsystems to show how each part functions.
The comparative subsystem converts the irregular sound signal input into a square wave output, which is much easier for the microcontroller to read. The subsystem does this by comparing the voltage from the sound signal to ground and outputting high whenever the voltage is above ground. The Zener diode ensures that the voltage input never exceeds 3.3 volts, since this would damage the microcontroller.
For building this subsystem, the comparator is an LM324 powered by 3.3 volts. The red line represents the 3.3 volt power from the microcontroller. The yellow line represents the input from the sound source. The white line represents the output to the microcontroller.
The transistor switch subsystem feeds the output for each color of LED into that line of LEDs. The subsystem does this by activating the base of the transistor whenever the LED should be on, allowing current to flow to the LEDs. The 100K ohm resistor inverts the signal, meaning that the LEDs receive 12 volts constantly, which drops to 0 volts upon the transistor switch closing.
For building this subsystem, the comparator is a NPN transistor. The white line represents the 3.3 volts input from the microcontroller. The yellow line represents the output to the line of LEDs.
The microcontroller used in this circuit runs code that digitally filters the input from the comparator subsystem and feeds it into the transistor switch subsystem. The code operates with a hardware interrupt, which activates upon a rising edge from the comparator subsystem output, and a software interrupt, which runs 40 times per second to update the LEDs. The code counts the time between rising edges of the input signal to calculate the frequency, and uses this number to determine which LEDs to turn on. It gradually shifts the color of the LEDs in that direction through the use of a switch statement that can only move once per cycle. The actual output signal is that of a duty cycle, which runs a percentage of the time to determine the brightness of each color of LED.
This is a picture of the complete circuit attached to the microcontroller. The power source, sound input, microcontroller power cable, and LED outputs are not shown. The following video will show the circuit functioning while Mozart is playing as the audio input. We now move on to the results of the circuit. This graph shows an oscilloscope image of the filtered and unfiltered audio signals. The yellow function shows the raw signal from the audio input. The blue function shows the filtered signal after passing through the comparator subsystem. This signal is much easier for the microcontroller to read as a rising edge.
This chart shows our measurements of frequency from the code at different input frequencies as generated by the frequency generator. The measurements are consistently high but mimic the actual frequency with enough accuracy to be capable of changing lights. For a more precise system, it will be important to improve the accuracy of the frequency measurement.
As we designed and implemented the circuit, it underwent a number of changes. The first change was switching from a relay-based voltage controller to a transistor-based one. This allowed for faster response times to the changing duty cycle into the LEDs. Another change was to remove capacitors from the LED inputs. These were intended to cause gradual change between light levels, but only cause the colors to veer towards white. Additionally, many changes were made to the code. The code originally counted rising edges over time to determine frequency, but this was found to be too inaccurate a method, and so time between rising edges was used. The code also at one point used a function to calculate duty cycles, but this produced erratically changing lights, and so the method of set light values that are shifted between was used.
This plot shows the current design's RGB values at different frequencies. The best way to improve the circuit would be to change these frequencies to match each song being played. Some songs, like classical music, operate largely on low frequencies, while others, like rock and roll, operate on higher frequencies. By changing this build plot to match each song's bit signals, it will produce lights that look better for each individual song.
The real-world applications of this technology are in light shows and similar events. By having a system that automatically changes based on frequency, light shows can be designed that work automatically for the music being played instead of needing to be individually designed for each performance. This saves on man hours and difficulty.
Thank you for watching our video on our digital filter to LED driver.